Yeah, welcome everyone to the second part of my presentation called From Basic Research to Tumor Diagnostics. It's in a way, as I've mentioned last time already, it's a summary of a long story that stretches over a decade or so about how we found from basic research into something that is applied. And the class, as I was preparing this lecture, I got this idea that it's probably from the outside, it will probably look pretty chaotic and pretty erratic, but this is also in a way how our path has been. So I've tried to make it a little bit more systematic, and I've tried to, and that means that some of the things that I will tell as if they happened one after the other in reality happened at the same time. But just to make it appear a little bit more logical and to make it possible to extract the learnings, the things that we have understood from it. I restructured everything a little bit. And so since I already talked about the last time, this the class had a first, or this lecture had a first part. And that first part is available on YouTube. Under this link, tinyurl.com, Springer Talk 2020, or there's a QR code, or you can write to me if you're interested in looking at the first part. The first part was mostly about the science, and I will here now recapitulate it in a very, very brief presentation. So what is the discovery that we made? And why is it important? why did we think at the time that it was an important thing to do? So this is a cell, this is a body cell, and this body cell has a mutation, and as a result, it makes a tumor-associated protein. So that's a protein that only occurs in the cancer cell. And all the cells in the body have mechanisms by which the proteins that are made in the cell are broken up into little fragments called peptides. And these peptides are grabbed by a protein, and that protein is called the MHC class 1 protein or molecule. And that protein takes these peptide fragments, this red pentagon here, takes it to the cell surface. And then at the cell surface comes the T cell of the immune system. And the T cell at its own surface carries something called a T cell receptor. And that T cell receptor, you can see this, that binds to this combination of the MHC molecule and the peptide. And if this recognition happens, then the T cell knows this is a peptide fragment that was derived from a tumor. And this is how the T cell knows that this cell is a part of a tumor, and then the T cell can do a number of things. It can, for example, it could kill the tumor cell. And this is the scientific background of the immune response against tumors. And you can imagine, or you can now appreciate, that these MHC class 1 proteins that I have worked on since 1992, that these MHC class 1 proteins actually play an important role in the immune response against tumors. And everyone who's interested in tumor immunology and tumor immunotherapy therefore should be interested in MHC class 1 molecules. Shameless pitch for the importance of MHC class 1. And now, the reason why, or the kind of discovery that we made had something to do with staining T cells. If you have in a patient, if in a patient you would like to make lots and lots of tumor-specific T cells that will go back in the patient and kill the tumor, then what you can do is you can take out the tumor, like I explained last time. You can take out the tumor. You can then, from that tumor, you can grow out the different T cells. Those are these colored balls. Those are the T cells that are already inside the tumor. Those T cells, then you can characterize, you can figure out which one of those T cells will actually bind to and kill the tumor cells. And then you grow those up and you put them right back in the tumor. And then the idea is that now they will kill the tumor. This is one of the possibilities of tumor immunotherapy. If you want to know more about this, it's called adoptive transfer. So how do you identify out of these many different cells, how do you identify the ones that react with a tumor? Well, we know this already. Those will be the cells that recognize these peptides in context with these MHC class 1 proteins. And so the idea was, this is now the most difficult scientific part, I hope I got this across last time. The idea is that you can actually then use these MHC proteins together with a peptide to stain the tumors, the T cells. Because the T cells with their T cell receptor, they will recognize and bind to that MHC peptide complex. So you attach a dye, and then if you throw this reagent here, if you throw this onto the T cells, then the T cells will become brightly stained with this fluorescent dye. Very beautiful. So then I also explained to you last time that in order to do this better, to get a tighter binding, you have these MHC tetramers that are made of actually 4 MHC molecules in some really complicated fashion, and they just bind much more tightly to the T cells. And then they can be used for this staining process, and the staining process I will today actually explain a little bit better. There's also going to be some science today. So, so these so-called tetramers, they solve the task of recognizing the correct T cells. So now, our discovery was that we made a disulfide stabilized MHC molecule from which you can make disulfide stabilized MHC tetramers. And remember that this allows us now to generate the patient-specific reagent within a few seconds. You just add the peptide and you can immediately stain. In the old system, before our invention was made, you needed several weeks because you had to add the peptide at the very beginning of this long and tedious procedure. I'm not going back into details, but the idea is we're going from weeks to seconds with our invention. So and we realized this the moment that we had invented this technology sometime back in 2011 or so, or end of 2010, beginning of 2011. But then we were faced with something, and this is where I ended last time, called the validation gap. So the validation gap is, of course, as a scientist with a paper, with a discovery, you stand here on this end, maybe this is us, and you think, wow, you know, this could be used in an application. This could be used to treat actual tumor patients. This could be used as a diagnostic tool. This could be so useful. But how do we get there? How do we get from A to B? So in order to, and that's of course what I'm going to want to talk about and to explain today. And I already explained, I already told you that you know, that the way that science works, the way that basic science works, is that you have funding, you do research, you generate data, you write a manuscript. The manuscript has to be published from here to here, can easily be a year or two, reviewing process and so on. Then you have a manuscript, then you can use those publications to apply for more grants, and then you get more money. So this kind of rotates all, and the better you are, the faster the rotation is, the better you are, the more money you burn and the more papers you generate. But where is application here? Where is validation? Where are patents? Where are companies? Where is money that's coming out of this? This is a cycle that eats cash to turn into papers. So how do you connect this with the actual world of application and transfer? The way that this is connected, and I will show this slide a lot today, the way that this is connected, of course, is that out of this cycle, you generate data that can constitute something that I would call a proof of concept. So it's something you say, that's where we are at the moment here in the talk, or where we were in 2011. I said, okay, you know, we've got something that we think is going to work as a product. But then, of course, you have to make sure, you have to see, you have to check whether have you actually got a patent? Yeah, is it actually is it useful to have, or is it necessary to have a patent? Yeah, we'll talk about patents in a moment. Do you actually have a product that will survive on the market, or is it just some exciting data point that will never turn actually into a product that you can never sell, that is not useful? And then, of course, from there you have to take the path. To a company. In our case, I will explain the alternatives a little bit, and then you can generate licenses, you can say sell the IP. But the most interesting thing, and you will see that we'll just keep coming back to this over and over and over again, is the question, these red arrows here, how are they going to be paid for? Who will pay for this? Who will pay for this? Because the funding that we receive from the funding agencies like DFG or so, this will only pay, of course, to turn this cycle here. And this will not normally pay to do any of this. So the big question is often, where does this come from? So let's take it one step by the other. I'll talk first about patenting, and then we come to everything else. So in the crossing of the validation gap, the first step was clearly patenting. The first step is this little cloud here, and this represents this patenting. Oh yeah, I must mention that the person who has guided basically through the entire process and who has represented the good spirit of transfer at Jacobs University clearly was Ronald Kieschnick, the head of research services. And I really have to say thank you very much to him for guiding through this entire process and for making the right decisions. That's made me very happy. And we've had to do with him, of course, we have to do with him all the time because he's also responsible for grants, but all of this would not have been possible without his support. And then, of course, the person, if you want to think about patents, if you want to write a patent at Jacobs, you talk to our patent attorney, Alexander Jeschke, who recently has also actually had a very nice channel on YouTube where you can listen to his short clips where he answers lots of interesting questions about patenting and how alien this patenting world appears to a life scientist. I can demonstrate to you with a few little excerpts from the process. So, of course, the first thing you have to do is you have to turn your invention into a patent claim. And just the language of this took me maybe a year or so to get used to. So I'm just reading to you one of the paragraphs. I know one should never read from slides, but today I will read from slides because it's so much fun. And this was, for example, just getting used to the language. So paragraph number 68, this was from one of our first applications. In addition to the helper ligand, or instead of the helper ligand, the folded protein preferably has a ligand exchanger / ligand releaser that has a lesser affinity with the receptor protein than the helper ligand and or is an amino acid or a peptide of 2, 3, 4, 5, 6, or 7, preferably 2 or 3 amino acids. A combination in which the helper ligand is a peptide of 8, 9, 10, or 11, for example, 9 or 10 amino acids, and the ligand exchanger / ligand releaser is a single amino acid or a peptide of 2, 3, 4, 5, 6, or 7, preferably 2 or 3 amino acids, is particularly preferred. So this language for a scientist is completely impenetrable. It's really, really, really difficult to read. And it's also, for me, it's really difficult to write. But if you don't write a proper patent, it won't be worth anything. Yeah. So it was very, very important to learn these things and to try to figure out how this goes. Yeah. It just becomes totally crazy. This is paragraph number 75. I'm not sure that I'm going to read this out now, maybe just the first sentence. A pre-solution examination reagent includes an exchangeable receptor protein complex, e.g. MHC class I protein complex, i.e. a folded receptor protein having a bonded helper ligand, or in another embodiment, a multimer having folded receptor proteins, e.g. MHC class I proteins featuring the helper ligand, or in another embodiment, a particle having, I think this sentence is just never going to end. So it is, over time, of course, you realize that patents have their own language. Yeah, that you can learn just like a language, just like probably French or Spanish or so. You can learn this, you can learn how to do this, but it's not something that you do on a Friday afternoon. And then, of course, you have to decide very carefully what you're going to claim. Yeah. So in the previous one was the description of the system as a whole, and this is the last section of this particular patent application. 1, 2, 3, 4, 5 pages of very carefully designed claims that are also written in a very abstract, formalized, complicated, interesting language. I'm not saying it doesn't make sense. I'm just saying that this is something that for the scientist is particularly hard to figure out. And so I spent a lot of time I think maybe for each patent, certainly dozens of hours trying to understand and trying to write and trying to read this kind of thing. But then when you think you're almost there and you've got your patent submitted to then of course comes the conversations, the communications with the different patenting agencies. For example, here the USPTO in the United States, that via our American lawyer communicates with us. Here you can see the name of the person who's examining the patent for the United States. And if you thought that the patent language is difficult, then read this. For example, this is part of this. This is part of a, I think, 16 or 17 page document that she sent to us. And it says, possession may not be shown by merely describing how to obtain possession of members of the claimed genus or how to identify their common structural features. See, and then this is another patent. Applicant is also reminded that the written description provision of 35 USC 112 is severable from its enablement provision. Yeah. So if you don't know what this means, then you're in trouble. Yeah. Luckily, we had two very good people to help us with this, the American patent attorney and Alexander Jeschke, and they took it apart for me, but it was an interesting, long, complicated, not easy, certainly, journey to get to this, and it took a lot of energy. So eventually, this is one example of one of our patents that got granted. And this is of course very beautiful if you see this happening, but there certainly was a lot of work behind it, and the amount of work you can guess perhaps from this, which is just a screenshot of one of my folders that deals with the procedures of just one of our patents. So this patent was applied for on the 14th of June in 2014. And eventually the patent was granted on the 23rd of December of 2016. So we have 2.5 years that this was going, and this was not like there was 2.5 years of nothing, but there were several communications with the USPTO, several rebuttals from us, phone conversations with the USPTO, and so on. And this is only for the United States. This is not for Europe or Germany or any of this. Yeah? And this is only for one of the patents. So you can imagine that patenting your claims can keep you pretty busy as a scientist. So what came out of this at the end, and this is also interesting, for a number of reasons. What came out of this is this kind of checkerboard pattern of patent protection. We had, let's say, for the sake of the argument, that we have two different separate patents. One of them is called, I will call here disulfides. The other one I will call dipeptides. And you can see that, for example, for this dipeptides patent, there is very good protection in Germany and the UK. There is no protection in the rest of Europe. There is relatively good protection, something in between in the US. There is no protection in China and Japan. For the other one is there's a limited protection in Germany. There is no protection in the rest of Europe. There is very good protection in the US, but there's no protection in China and Japan. So you can ask yourself, you know, what did you do there? What went wrong? What happened? Yeah. And well, one of the things, for example, here in the US, this patent we didn't get granted the way we wanted. Yeah, there were so many, it was contradicted so many times by the USPTO, and we had to reduce the claims and keep reducing them, and so they don't, now those claims don't look so good anymore on the paper. But it's not such a big problem, because for our technology that I've described for the disulfide stabilized class 1 proteins, you actually need to be able to apply both patents. So this means that, for example, Germany and UK have good, overall good patent protection, the US protection, but the rest of Europe and China, there was nothing. And the reason why was that? Why is that? Why didn't we do anything? Well, for the rest of Europe, we have to imagine that the patent protection, you know, actually costs money. Yeah, the applications cost money, but especially the maintenance of the patents is expensive, and so you cannot just protect everything everywhere. You have to make very careful decisions about what to do where and how to do this best. And so this means that in our case, for example, France, Italy, we just never maintained the patents. China and Japan, I think we, as far as I remember, I think we didn't even apply. China and Japan are special in a way that I will come back to later. Yeah, so you never get perfect protection for everything everywhere because of financial, organizational reasons, and maybe perhaps the patent agencies don't like that. They don't like you enough, and then you don't get what you want. But okay, you know, I mean, in any case, we have arrived here. Who paid for this? Red Arrow. Who paid for this? Jacobs paid for it. Jacobs paid for it because they, you know, because they believed that something would eventually come out of this, so they could get their they could get their costs back. Now, the second step, of course, in the validation process would then be to make sure that you have a marketable product, not just in some kind of exciting data point and say, oh yeah, in principle, this should be great. What a great reagent, should be fantastic. But something that you can actually convince someone, oh wow, you know, this is something you want to sell. This is something you want to get in the market. Yeah. And so the second step of this validation process is clearly to generate a marketable product. And the problem is, again, you know, the red arrow, who's going to pay for this? And here, this is going to be much, much more expensive than this. If you think, okay, you know, it's going to be about a year for 2 people to get this right to a point where you can say, okay, we can sell this now. We have a product. Well, two people for a year would be about 150,000 euros. Yeah. So where do you get the money from? Where should it come from? Where should this? Who would pay for this? Well, certainly not the funding agencies, because the funding agencies, they're only concerned in turning this wheel here. And if you take the money and you invest it over here, then later on you won't have enough data to generate new papers, and then you will not get any new grants, and the circle will stop. So it's obvious from the amounts of money that a small company, like one of the little biotech companies in Bremen that have just 3 or 4 people or so, that a small company would never be able to pay for the validation of this. And so what I did, I would say pretty naively, what I did is I just looked on the internet and I said, okay, which of the companies that exist in reality, which of the companies that exist that already sell tetramers would be interested in taking advantage of this fantastic innovation and turn it into a product and sell it themselves. That was my idea. And so there's a whole bunch of companies in the market who are selling tetramers. All of those are companies that are now still also selling tetramers. And those are some of the companies that I wrote a letter to. And I wrote and I said, dear Chief Executive Officer, we have this fantastic new idea. I can't tell you very much about it, but if you buy this from us, or if you agree to develop it with us, you can get an exclusive license to the use of the technology afterwards. And very surprisingly for me, it's interesting, very surprisingly for me, not a single person replied to these letters or emails or calls. Not a single one of the companies altogether, maybe there were 6 or 7 or so, I did not receive a single reply. There was nothing, nobody was interested or maybe they were interested, but in any case, nobody replied. And then eventually I started talking to people at trade shows or at meetings, and I tried to call people and I tried to activate my network over LinkedIn, and I tried to talk to people to get them into helping me, providing cash to help me develop the product into something that would be saleable. And I got 2 different kinds of answers eventually that I want to share with you. And the first one, again, is a letter from the CSO of a Californian medium-sized company that I want to share with you. It's very interesting. He says, for any collaboration to be successful, it has to work for both sides. In academia, there might be the perception that there's an endless supply of money in industry. That's really not correct. Everywhere I worked, budgets are tight and you're always told to be creative and do more for less. Not different from academia, really. So we do count pennies too. We know what it costs to develop or run an assay. If we can do it ourselves faster or cheaper, we're likely to choose that route. To start a collaboration with any partner, academic or industry, it's also good to realize that the research team will typically not get additional budget for exploratory work. We would be required to cut something away in our own budget, but still reach the same goals by the end of the year. So collaborations are often in direct competition with internal research funding. In those settings, you really need to make a very strong argument that a collab makes a massive contribution to research program that yields results at the end of the year, that we're A, on top of what is expected, or B, so totally mind-blowing that all other results no longer matter, kind of unlikely. So this means this person, for example, was unwilling to enter into a development cooperation because he says, this is just going to eat, the collaboration with you is just going to eat into my own research budget. Why should I do this? Yeah. Why should this help me? Why shouldn't I do what I'm supposed to do anyways? That was answer number 1. I thought it's very interesting. This is not what you think when you're an academic scientist. You really do think as an academic scientist that companies have unlimited amounts of cash. And the second one was from a German company that maybe Alexander will recognize, I don't know. It's a German medium-sized company, and we were hashing out with them a joint development contract so that we were going to do some contract research for them. And again, I must read this to you. It basically, well, actually, the first paragraph basically says that that any of the IP, any of the intellectual property that is generated during the work together belongs half to the company and half to the university. And then this paragraph down here says, university shall grant to the company an exclusive royalty-free, sub-licensable, and worldwide right and license for all users under the technology to the extent necessary for the company to use the joint IP. So this basically means, it basically says that if we help you develop the stuff, then we will own half of the patents, and you will never get any money from it. You will never get anything out of this financially. Yeah. And then really you ask yourself, then what's the point of this? Why should I do this? Why should I work with this company if, afterwards they're just going to have everything? And what does the university get? What's the university get who's looked after the patents? What do they get? Yeah. And Jacobs pays my salary. What are they getting? yeah, then basically we work, the company gets the results, and what do we get? What does the university get? This makes no sense. This kind of collaboration makes no sense. Then it's better to go it alone. Then the next one is about the PhD students. I have a slide here about PhD students who are really complex human beings with hopes, dreams, and aspirations. We most frequently reduce them just to brains and a pair of hands. But the joke aside, perhaps, interesting question with a collaboration with industry that involves PhD students is the following. The PhD students, over time, over the years, they become more and more and more productive. In the beginning, they just have to learn so much. There's so much that they have to do, they have to learn, they have to come up with, and this makes sense. There's nothing wrong with this. This is perfectly fine. But they're really only productive towards the end of their time during the PhD phase. And so of course, this is what you would wish. You would wish for a company to fund the PhD all the way through, from the very beginning to the very end. But of course, what the company wants is they want to fund just at the very, very end when the productivity is really very high. So then the question is, who pays for the training? Who pays for the training of the people? If the company just want the short time when everything is super efficient and super great and works fantastically, who is going to pay? Who is going to pay for the training of the people? And this is when I realized for the first time that if you want to work with companies, at least in our field, if you want to work with companies, you must keep a strong basic science background. You must continue to get DFG grants and basic grants, because otherwise you will never have people, you will never have equipment, you will never have the level of expertise that the company wants when they eventually come in and they want to get results from you. Of course, they want you to have trained, experienced people, and not someone who's just starting out and who's learning the ropes and who's going to take a year or 2 years before they get into the red zone. Yeah. So this also means if you as a basic scientist like me, if I rely on companies 100% to fund my research, it's likely to crash. So at the end of this part, what I want to share with you is that I also talked to two old friends of mine who are now very senior people in a large Swiss pharmaceutical company. And this is a person who was a student, actually a fellow first year, a student of biochemistry in Tübingen with me. And this is somebody, this is his colleague, and I talked to them in a phone call, and they said to me, we at XY, large Swiss pharmaceutical company, we don't support some professor who has some fancy ideas. Yeah, the only thing we do is we buy companies. If you have a company that's interesting and that's running and the product is fine and everything is good, yeah, then we will consider buying your company. But otherwise, I'm sorry, this is not going to happen. No. And then I said, but why is this? And he said, well, we have some professor calling every day with some idea. Yeah, we don't have time. It would just completely distract us to try to check on all of these things. Yeah, once you have demonstrated that you have a company that is working, we can buy it off you, perhaps. Okay, so I realized we realized for the first time here that it might be necessary, in fact, to try to set up our own company, but we weren't there yet. We didn't have anything. We didn't have any validation. Yeah. And so then finally we thought, okay, maybe there is a possibility to get validation funding through the schemes of the BMBF or the BMWE. They have funding schemes called KMU Innovativ or ZIN, and their idea is to give a little bit of money to allow people to turn an idea into a company. And this at the time did not work out because both of these schemes require one collaborator from the group or from the outside perhaps to turn into an entrepreneur and to run this company, to actually set up a company and to start running it. And this at the time for us was not possible, because the only person who would have been possible for this spoke no German whatsoever. And without German, I think participation in these schemes is really quite difficult. So I thought for a while, should I give up my professorship and should I move on and set up my own company with this? But I didn't, and it turns out that it was a good idea not to do that. So at this point in time, we were stuck between here and here. We couldn't really get to anywhere. And during this time, one little positive thing happened. One company called us and asked and told us that they would be interested in taking a license for one of the patents. And this they got, and they started selling the part, let's say, part of our invention, something that you can, if you're a scientist and if you're interested, you can look this up. It now allows the exchange of peptides, not really disulfide stabilization, but the exchange of peptides. And this is a product that since then on their website has been going reasonably well. But for Jacobs University, it's not generating a lot of revenue at the moment, at least. So then what happened? So this was fine. It was a bit of an uptick. It was some sort of light at the end of the tunnel, but there wasn't very much forthcoming. It wasn't very. It was clear that this was only enough to cover the costs, and we weren't making any money, and we weren't getting anywhere. And then eventually, what happened was that our funding, to continue to develop the system, ran out, and then basically we couldn't do anything anymore. And we sat there, and we had no more money to turn the wheel, no more money to generate any new data or anything in addition, and we also had no more money to move on from here to here, for example. Then, of course, in that situation, we were very lucky that Jacobs helped out with a position, with a time-limited position. This was very useful and very helpful for us. I can't talk about it here in detail. But the real breakthrough towards the validation came through one of our PhD graduates, and this was Sunil, who graduated maybe in, I think, 14 or so, or 15. And afterwards, he went to a laboratory in Denmark that was run by a rather young person, Sine Herdrup. And she is a person who actually specializes in tumor and virus immunotherapy. And one day, she asked Sunil what he had been doing in my lab, and Sunil explained about the disulfide mutants and about all these things, and then she agreed, or she saw, or she understood that just like we did, that this was an exciting opportunity, that this is something that we should do. Yeah, or that she would like to try. And the difference between her and us is that, you know, we are only able to do this, but she in her lab is able to do this entire thing. And so as a result of this, she can do the whole process. She can validate, she can show that the tetramer reagents work in this actual process. And this is something that we ourselves were not able to do, and that we also didn't manage to get funding for, as I spent a half an hour explaining to you. So what are the tasks in the validation? What are the scientific tasks in the validation of this invention? Well, you know, here you have, let's go back here. You have these different T cells. There are green ones and yellow ones and blue ones, and only these are the ones that you want. quick recapitulation. How are they different? The yellow ones, the blue ones, and the green ones, they're different from the different types of T cell receptor that they carry at their cell surface. They can be found, the right ones can be identified with the help of these MHC tetramers. And then, of course, in order to be able to validate this, you have to demonstrate that the disulfide stabilized class 1 tetramers, that they have the same, they bind to the same T cell receptors, not to some other ones. And that they are specific for the same T cell receptors, that they don't bind to some other T cells, and that they bind with the same strength, with the same affinity. Why do you have to show this? Because otherwise, in this step, the selection will not work properly, and then they are worthless. So basically, you have to convince the skeptical scientists and doctors that these tetramers in that assay perform in exactly the same way as what the scientists call the wild type, the normal class 1 molecules. And so I'm going to just share a few scientific data, not so much, the time is already progressed. But I don't even think I need to explain in the greatest of details exactly what this is. This is an affinity measurement. So it shows how tightly does the class 1 tetramer bind to the T cell receptor. And down here, this is our disulfide stabilized molecule. Up here, this is the wild type, the unchanged, the original, the normal one. And you can see that these curves, they look very, very, very similar. Yeah? And that made us very happy. So it shows that the binding of the MHC class 1 tetramer and the T cell receptor was pretty much the same. And these so-called binding affinities, they're plotted here against each other on the x-axis for the disulfide stabilized, on the y-axis for the wild type. Each dot is one MHC class 1 molecule with one particular peptide. You can see that all the values are pretty much on the diagonal. This is because the two affinities have the same values. Then they should be on the diagonal. So this demonstrates for 140 different peptide MHC complexes that the binding affinity is spot on. That, of course, made us really, really happy. And of course, in addition to this, Sine and Sunil did a lot more work. These are just some of the figures that from a publication that show how many assays they did and how much work this validation was. And that was done pretty much only by the two of them. And this made me especially happy here. Those were, this is a little assay done with the T cells of an actual cancer patient. And you can see here that the disulfide stabilized tetramers, they work just as well as the wild type ones. In fact, it turns out that the disulfide stabilized tetramers actually work even a little bit better. So you can see here that in this plot, the cells that are stained, they are like a rocket, right? They are departing here from this purple blob. Yeah. So those are the cells that are stained. Those are the cells that are not stained. You can see that the difference here between them is much greater than the difference down here. And this tells you that our disulfide stabilized tetramers, because they're more stable and they're generally happier, they are the better staining reagents. They're not just more convenient, they're also even better. And this is what Sunil and Sine in Copenhagen found out. And that, of course, made me very happy. So then we went on with a different set of collaborators in the meantime to also make a crystal structure of these proteins. And we can do crystal structures at the DESY, the German electron synchrotron in Hamburg. There is an so-called outstation of the European Molecular Biology Laboratory, and the two leaders of this outstation, Rob Myers and Maria Garcia. And a lot of that work was done at Jacobs, and then the rest of the work, the crystallization of the proteins, the X-ray irradiation, and the determination of the structure, this was done by these two people in Hamburg. And perhaps it's a good idea to keep in mind these enormous timelines that you have in science. Yeah? When you work in business, your timeline is something like 6 months. Yeah. So for example, one of the reasons, if I just go back, one of the reasons why this arrow was so incredibly short is that also the people at the company in Germany said, well, you know, we can't, our financial horizon is not longer than 6 months. We can't guarantee or promise anything that is longer than 6 months. We can't give you a PhD grant for 3 or 4 years. This is totally impossible because we're not able to look into the future for more than 6 months. Yeah. So to put this into perspective a little bit, this process here, the collaboration with Rob Meyer, started in 2012, in January of 2012, and the results were obtained at the end of 2018. So we have at least 6 years, more closer to 7 years that we have worked on this. Yeah. And eventually, this was the result of that collaboration. So what you see here in my little sign language is the MHC class 1 protein at the bottom and the T cell receptor at the top. If we transfer it to over here, this is the MHC class 1 molecule at the bottom, and this is the T cell receptor at the top that is rotating here. And if I'm and what are you supposed to see here in this diagram? You're supposed to see the disulfide bond that is here where my red dot is, this little yellow object. And you can see how far away this is from the place where the T cell receptor binds. And that means that the disulfide bond is not in the way of the T cell receptor. And this is why, this is the molecular reason why these disulfide stabilized mutants are actually fine. They're actually really good for using just like normal class 1 molecules. So with that, of course, we were very lucky, we were very happy. There's a lot of interesting additional science. And it was important for us that then in the last year, the results of these validation experiments from Sina's lab and from a company that we also work with were published in a very prominent journal. And this has been very, very, very helpful later on in the validation. So it's not like papers don't help in the validation of scientific results. In this case, we can always, if somebody comes and says, oh, but you know, how do we know that your things work? And how do we know? And how do we know? And you can say, well, you know, it's all published here. Yeah. So without these publications, without the people who worked on this, without these collaborations, some of which have gone back almost 10 years, without this, the next step would never have been possible. And that next step now, this is the final part also of the presentation. I think I've just got about 5 to 10 slides left. The final part of this was the actual transfer. This means actually setting up licenses and trying to figure out how to set up our own company. It was clear to us at this point that we would not be able to turn over this technology to a company. But now, since we knew the people in Copenhagen, we weren't afraid anymore of setting up our own. And of course, one person who's been extremely helpful and instrumental, very, very important in this process was Alexander Ziegler-Jöns, the CEO of the Jacobs JCBS holding, without whom we probably would have made a lot of decisions that were imprudent. Yeah. So thank you very much, Alexander. What we realized in the very beginning is that with the company that we would set up, we would have to be close to the application and the practical experience, spatially close, in close physical proximity. And so that meant the candidates for this were the DTU, the Danish Technical University in Copenhagen, or else the Karolinska Institute in Stockholm. And for some time we were talking to both of these, whether in their vicinity somewhere we would be able to set up a company where this entire cycle of immunotherapy was done and where people would be able to test our products and to expand them and to demonstrate that they work and all of these things. And so that's one of the reasons why now eventually the company did not end up actually being in Bremen. No? So one of the very interesting things, perhaps when I was in Karolinska to talk to the people there, at the Karolinska Innovations, which is the tech transfer agency of the Karolinska Institute, was that the people there told me that you know, you really have to have a decent understanding of these 4 fields in order to get anything that is medical or diagnostic to the market. You need to know about the science, of course, but the science is not everything. You think as a professor, if you got the science, then you got it. If you got science, you got one out of 4. You need to know about patent law, this I told you about. You need to know about medicine, because you need to know where's the application. You need to know where's the market. And of course, you need to know about business. And so I'll talk to, and this is in that intersection here, this is where companies are generated. So I want to tell you a tiny little bit about business. This is an internal rate of return table. And this is something that we use to try to figure out if we should get investment from the outside of the company. So should we accept like €1 million maybe from investors in order to make a big company at the very start? And the way to read this table is the following. If you imagine you are the investor, the investor company was called Dianova. Imagine you're the investor company. You want, and let's assume you want to put in your capital, like maybe you want your capital back after 4 years. Maybe you want your capital back after 4 years. And you want to generate an overall gain of 32% on your capital per year. That's called the internal rate of return. And this is 30% is approximately what such investment companies aim for. They aim to increase their money, their capital by about 30% per year. That means that if you're growing 30% per year and you want to keep it for 4 years, this means that during this time, the value of the money that you put into the company has to have tripled. This means basically you're giving to the company €1 million, and after 4 years, you want €3 million back. This means the company that you finance in the meantime has got to triple the money. So this is, and that sounds kind of okay, but you have to take another important thing into account when you talk to investors, and that is the venture return chart. Venture return chart means how much money do investors actually get back from investments. And it turns out that, so 1.0x is the amount of money that you put in, yeah, and so the learning from this chart is that 65%, 2/3 of companies, from 2/3 of the companies, in the end, you don't actually get your money back. You either get nothing back or you just about get your investment back. Anything in between there is 65%. That means that the remaining third, 1/3 of the companies that you invest in have to generate this return rate. They have to generate this return. And this means that, of course, for those companies that actually return, you don't need a threefold return, you need a 9-fold return. Yeah. So in order for the investor to achieve their internal rate of return of 32%, they need to give you €1 million, and after 4 years, they need not 3, but they need €9 million back from you. And this is something that as a small startup company is just really, really difficult to realize. Yeah. And so when we decided to, this is when we realized this, then we decided, okay, we don't want to grow that aggressively that we say we want to grow by a factor of 10 in 4 years. Yeah, we want to take it more easily, and that meant for us that we had to find our own money to invest. And in order to keep the financial involvement relatively low, what we decided to do instead was that we would externalize as much of the procedure as possible. That means we would purchase our raw materials somewhere else, the proteins, we would have them made somewhere else. We would process them, all of this process that I told you before, the production process, we would do this not in the company itself, but we would rent space in the lab of Sina Haddock to have these proteins made or processed. So basically that we would purchase, or we would just supervise the production of the products, and we would only, and the company itself would only ship and not actually produce itself. And it would advertise, it would organize the distribution in different countries, and it would of course be involved in the customer service. And this business model means that if there are no orders, you have no costs. Because if there are no orders, you don't produce and you don't purchase. So this means that even if you grow slowly, even if times are bad, if you have a corona virus crisis or any of this, you can still keep going because you don't have a lot of expenses. And this was mostly the idea, the way to do this was mostly the idea of Søren Niveau Jacobsen, who is our chief executive officer, and whom we managed to get out of another company, basically, that also deals with tetramers. So he has a very much experience of the market, but he's also a very good nose of how to run this company in the market that exists. Maybe some people remember that this is actually Tripti, Sunil's wife, who is not working, she's not in the company, but she's involved in the production processes in Sina's lab. And so, in that way, the company was set up to do this. We didn't need so terribly much money, and we decided to split the funding, the funding of the company. Some of it was paid for by Sine, some of it was paid for by Sunil, some of it was paid for by myself, some of it was paid for by Søren, and Jacobs University also holds part of it and receives, of course, licenses, because the company is not only part owned by Jacobs, but it also pays license fees to Jacobs University. And those license fees are much more significant than what we're getting from the licensees of the other company. So then the interesting question is, after we have patent and validation and transfer, we can actually now cross to the other side. And as we cross to the other side, the difficulties, of course, don't end, because now you're standing there, you've gone through the red door, and you're standing there and you think, oh, what will happen next? And such a company, one could, in principle, one could grow it slowly, as we're doing now. One could grow it aggressively, but then we would, of course, have to take investors on board, and we would then have very different strategies of growing. Or eventually, one could just take the company and sell it to a big company, just like I told you before. Interesting question for me: will it ever happen that the licenses and the sale of IP will actually fund the research work in my own laboratory? That's, of course, is a beautiful dream, and at the moment I don't see yet whether this will happen. Ask me in a few years, we're going to have to see what comes of it. At the very end, I want to answer two questions that I've asked myself a lot. And the first question is, what are universities actually good for in this process? Apart from being strikingly beautiful, exciting in terms of lab research, and very good for a lot of young people, what do they do for this process? And I think I've learned in this process, like the Californian CSO said that I quoted to you earlier, in the academic setting, the priority is exploration, and in industry, there's a priority to reach preset results. Or to translate this in the language of the scientists, industry and university don't have the same goals, and they don't have the same aims. And there are so many things that companies can't do because they're tied to their preset results. It's our job. We are supposed to be exploratory and innovative. And it's our job to come up with new ideas, to be at the forefront and to bring in new and exciting stuff. And I would have never thought that companies that are so big and so powerful, that they often don't have the organization or the flexibility or the mobility to come up with new and innovative results. That for me was really a surprise. And this is something that we as a university can do. We can do crazy things. We're allowed to do things that fail and go wrong. We're allowed to do high risk projects that are high gain. And so maybe this is, if I could talk to my colleagues here, I would say that this is really something that we ought to be doing. We ought to be doing high risk, high gain projects that are innovative and crazy, because industry will not be able to do this, at least not if they continue to be like this. And the second thing is, what is it that I would recommend to the university? Because the university at the moment is going through a restructuring process, a strategy process, where the university is thinking about, who are we and what should we be doing? And my learning from this was, in order that, at least in our fields, in order to have transfer, you must have basic science, because otherwise this wheel of result generation is not turning, and that's not going to come from industry anytime soon. So in order to generate innovative, crazy results, you need to be able to do basic science. This is absolutely necessary. And a little bit of what the university can do and is doing already, networking between colleagues also, networking, contacts to industry, is always something that is necessary, interesting, important. Even though here in the Bremen area, maybe the results are pretty limited, but in general, it's always, maybe Germany-wide, yeah, it's definitely is a good idea. And the other thing that's a little bit unexpected are the master programs. That the master programs are important because, to some extent, they're a little bit outside of this wheel. The master students, they work often without funding from the DFG, and their projects don't need a lot of money, and so the master students can do a lot of exploratory work that is not always tied to the needs of the wheel. They can do exploration work. They can do validation work. They could even do some work that's connected with companies. So to an extent that PhD students that are funded out of this will never be able to do. And that's why I'm a real fan of master students. I'm a fan of master programs. And I think this is definitely what is necessary. It's already 2:03, so I would just like to say thank you to all the very many people who helped and supported and generated the data, and the funding agencies. Special thanks to Jacobs University. Just realized that I have not mentioned Stefan Kuhlmann, who for me was a very encouraging factor within administration. And he's also not on the slide here. But I would like to thank everyone I mentioned and I didn't mention. I'd like to thank you for your patience. And I'm very happy if anybody would like to take any questions that might remain. Thank you very much.